Good afternoon. My name is Phil Myers. I'm the product manager at SAM, looking after our IP products. I'm going to run you through one of our case studies for a project we installed actually at the back end of last year, and we're currently phasing to on air at the moment. And it's a project at BCE in Luxembourg. So RTL is the end customer. It's a very large European broadcaster. BCE is the in-house systems integrator for RTL, so manages all of its projects. And essentially, the RTL has a number of businesses across Europe, telco, broadcasting, and a number of services it provides to a number of customers. So the RTL group has, like I said, it's up to 60 channels on air currently around Europe, 31 radio stations, very large broadcaster. And in 2013, they made a decision to move to a new facility, so the RTL City project. And this is essentially to consolidate a number of buildings into one. So one of the key things here was really they realized that they had to move to a facility that would allow them to expand in the future and give them a greater flexibility with the technology. And as you can see, it's a fairly large investment in terms of the facility. Like I said, the decision was taken in 2013. And the site that they're currently in at the moment in Luxembourg will be redeveloped once they move into their new site. So the project requirement is really simple. The technology they want to put into this new facility has to have a shelf life well and beyond the installation date. And what they're really looking here really is around 10 years post-build. And they, if possible, at the time when they were looking at the technology available, they wanted to make as much of this as possible to be IP. So whether that's -6 with -7 redundancy, AS67 for your audio, or PTP for your timing. And they had, at the time, a bit of a preference towards a spinal leaf network topology. But most importantly, at the time, it had to be future-ready for VSF TR03, so elementary stream-based flows. BCE did work with IRT, who provided quite a lot of consultancy. So Marcus Berg and the team at IRT Munich supported this quite extensively. And a lot of the findings from them, they presented back into BCE. It's a phase-based project. Like I said, it's not just studios, it's also playout and the core infrastructure as well. So it's quite a lot of equipment that needs to be transitioned. And the date for on air is early this year, and we're currently running out the phase of that project now. So the concept really was really simple. Flexibility to be able to add more capacity, spin up more channels in terms of player if where required. Really important to move from where they are today. So when you look at RTL, they have a lot of SD and HD channels, but be able to move to 1080p, whether that's to facilitate UHD or whether it's to facilitate HDR in the future, and also to bring some cost savings, whether that's consolidation of signals onto individual cables in a network design. But I guess the key other drivers really are enabling the virtualization of services. So to take a lot of services that are currently used to running on dedicated tin and consolidating them down onto a virtual platform. But this is really an important thing, which is whatever they put in has to be highly reliable and has to be as good as what they're replacing. And that's actually one of the key things for them. And really, they wanted to be no limitation on single vendor. So one of the things that's really nice about IP is it allows customers to choose best in breed, to be able to choose multiple vendors to come together in one IP solution. So for them, they did have a set number of technical criteria in terms of the technology, had to be standards-based, had to allow them to services and maintain it through an expanded team within their organization, and also take advantage of some of the COTS IT technology that's available in the marketplace. So they did have a timeline, quite an aggressive timeline. So they started the original concept back in November 2014. That ran through 2015, engaging with many suppliers, looking at what technology was available in the marketplace, looking at what could and what couldn't be done. And essentially, they ran a POC in the summer of 2015 to really get a better feel of what was possible. At September in 2015, IRT ran a proof of interoperability with a select number of manufacturers to also drill down really to actually make sure the criteria that was required by BCE and RTL was going to be met by the vendors that were going to be chosen. So the proof of interoperability is really simple. There's a number of set criteria they put down, which was -6 for your video and audio essence with -7 hitless protection switching. How would the system behave when it was doing clean switching? How would it behave when it was doing dirty switching? How would it recover? In the audio interoperability, so when you're looking at a large IP facility, how are we going to bring audio into the system? And how are we going to time it all up? So, how are we going to align everything in the system? And then, in terms of the kind of the connectivity, was having the ability to look at multiple COTS vendors, and then look at whether you have a singular overarching control system, or whether you have a two-tiered approach where you have an overarching control system and then individual vendors SDN running underneath it. So IRT presented this back last year, and it really gives you a key understanding of where they got to as part of their interoperability. So one of the key messages was that at the time when they looked at the technology that was available, 2022-6 was very interoperable. Pretty much every vendor that could turn up could plug up and they could move streams. Dash 7 was implemented by some vendors, but not by every vendor. And AS67 with PDP had quite a bit of way to go at that point in time. So essentially, as you kind of run down the list, you look at there was quite a number of things that they had to go back and reevaluate before they could make a decision on where they wanted to get to. So I guess really at this point, the general conclusion was that the technology wasn't fully mature and further investigation was required. So another POC was run later in that year, really to look at the findings of the IRT proof of interoperability, and again, realign them with the requirements of the customer to make sure that they're going to deliver the customer's ultimate solution. Sam participated in that phase. We put forward a number of solutions for gateways across the facility, for the COTS routing, production switches and servers. And one of the things that we had to prove when we moved to the next stage when we awarded the contract is to make sure that you can scale it. POC is very different to deploying a very large core IP infrastructure project. So when you kind of look at a normal facility, you end up with quite a lot of devices that have a lot of connections going to a core SDI router. And in most cases, you might find that actually you need to have large amounts of conversion. And in an IP environment, you might actually have some native IP devices, okay? So what we proposed was consolidating some of the devices and running two core COTS switches for both Arista and Juniper. And we centralized the switches. So instead of looking at the original design where you move the leaves up to the levels and you have a core spine, actually the decision was taken when you look at the number of signals that need to move around was actually to use long-range optics to the devices from the core routing infrastructure. So audio mux and demux was required. Audio breakaways is quite a fundamental requirement for these types of projects. And we deployed a mixture of 10 gig and 40 gig native devices. So it does bring a number of technical challenges, and it's good to be aware of them. All these projects do have a lot of these challenges. The network topology and connectivity is one of them. Without the right net topology and connectivity, it's very hard to build up a solid foundation. System timing, how are we going to time everything up in the system to make sure that we can move things around, we can clean switch, we can make sure audio and video is absolutely accurate. For this project, the customer was insisting on TRO4 from the start, so 2022-6 for the audio and video, but also having a separate audio stream to be able to allow us to do things like audio breakaway. And one of the key things was the switching performance in a COTS switch. So when we talk about COTS switches, what we're really talking about is enterprise-class COTS switches to make sure they're truly non-blocking. Everything must be able to come in and must be able to go out in this type of solution. And at the time, the customer wanted to be able to see a migration path on air to be able to go to VSF TR03 or 2110 when ratified. And I guess this is the really important thing. So when you're building a large IP system, you need to have visibility of the system. And that's actually one of the benefits that moving to IP does. It allows us to monitor the system very, very accurately. But also we need to have a control system which allows the user to not have to understand what the technology is that underpins it. So let's go through the first one. So like I said, network connectivity was based on 40 gig products. So we provided gateways, production switcher on 40 gig. There was a number of third-party IP native devices in the system which were 10 gig based. And we essentially built a 40 gig core switch, and we broke out all of the 10 gigs directly from the 40 gig ports. So this gives you really maximum density on your network core. In terms of the switching or the core switches, you probably noticed that we had two separate switches from two separate vendors. And this was by choice for the customer. So where most customers would maybe have the same vendor, one of the things that does bring in, if you have a software issue that rises up further down the line after you've done the upgrade, it's likely if you have the same switch and you have the same software, you might run into on your redundancy. So it's quite common in the telcos market that you might find that you have two separate switches from two separate vendors. This does bring a challenge because the switch vendors are very, very different in terms of the throughput that goes through these switches in terms of the speed of the data plane. So it's required for 22-7 redundancy. And what we have essentially are the flows. Each device transmits the data on both networks. So in this case, the Juniper and the Arista gets the traffic, and the receiver receives both lanes of traffic. And in traditional SDI world, you'd have a kind of failover switch to move from one path to the next. In an IP world, we don't worry about it. It's actually the receiver that arbitrates which packet it takes because it's receiving both of them. Okay, so you are truly in an active environment. And typically, if you're running our receivers in frame sync mode, you'll have up to 1 frame of buffer available at the destination, which will also help you align if you've got sources coming through multiple hops to the destination. Like I said, packets are received and joined and merged at the destination. The next thing is looking at a monolithic switch versus a spinal leaf topology. So in a monolithic switch with the new cell-based forwarding fabrics, we can essentially build a large non-blocking switch with high port density. So when you look at switches like the 7508 from Arista or the Juniper switch, you can get a lot of line cards into these switches and up to port speeds of 100 gig. So it moves away a lot of the complexity and potential issues around hashing or moving flows up and down spines without any management. And like I said, we deployed long-range optics, which does bring in additional cost. So you have to really weigh out where your devices are that you're going to be routing your signals to. So system timing is really key and important. So as part keeping the system timed up properly, we had redundant Tektronix SPG 8000s. And typically what we find with all the type of IP projects we're deploying at the moment, along with the BCE project, is that you still have tri-level and black burst requirements. There's still legacy to products in the system. And actually in this system, you do have Grass Valley cameras, which at the time don't currently support PDP, so we have to reference them up. So the Tektronix are doing two things. They're providing the Grandmaster, but they're also providing the black and burst and tri-level timing as well. But because we've got a lot of slaves in the network, we're actually using a couple of Mindbergs to distribute the PDP down through the switches to the edge devices. Everything's based on 2059-2 profiles for PDP, and we're essentially transparently passing it down to the edge device. Okay. Boundary clock was investigated, but it was not considered, mainly due to around the roadmaps of the, implementation on these COT switches at the time. As we move forward this year, you're going to see a lot of the COT switch vendors start implementing PDP directly on their switches. So what does that look like? Well, you end up with a Tektronix that locks a GPS. The Tektronix can serve up a handful of slaves, but when you have a large facility with a lot of slaves, it needs a little bit of help. So if you think about a black and burst environment, you'd have your main SPG and you'd have a DA that would then fan it out to your clients. It's slightly similar to that. The camera would take the black and burst because it has a legacy connectivity. The timing goes down to our gateways through the switch, to our production switcher as well. So we do multicast down to the devices, and then we're doing unicast response back up to the Grandmaster. This way we kind of reduce a lot of the traffic that's in the network, and then hopefully protects also some of our edge devices. And this is PDP hybrid mode. So implementing TR4 was fairly straightforward. It's fairly well documented in terms of being able to implement. So we have 2020-6, like I said, for the audio-video essence. You can then have a separate audio stream, which can come from a MADI to IP gateway or from another SDI to get IP gateway, and we can bring the two together at the destination. But there are some set requirements in terms of the number of channels of audio and also the packet latency that's required. But this is actually quite an important thing. So if you have a lot of audio in the system and you need to be able to do shuffling, or you need to be able to do reordering of tracks, or taking multiple AS67 streams to one edge receiver, then you need some sort of device in the network to be able to allow you to do that. So the way we work that through is so you can have SDI, so it goes into our gateway. We put the essentially the connection to the network. We take the -6 to the receiver, and we can take the AS67 directly to the receiver. So SDI goes in, we demux it, and then we move it to the receiver, we mux it, and we go back out, okay? But if I want to take audio from somewhere else, like, for example, a MADI interface, then I take the video from one path, I take the audio from the second path. But one of the key things here is that the AS67 MADI stream has 64 channels, but your receiver is bound by the SDI standard, so it only takes 16. So in this case, we take the first 16, or we can shuffle those around in the order. However, if you want to have multiple audio, for example, where audio comes from separate streams, then we have to do something slightly different. So in this case, if I want this guy's audio with this guy's audio, I have to break the first connection, okay? So what we've done is we've introduced something called an audio access. It's a COTS, a server that sits in the network. And essentially, it's a software-based IP audio router. So it takes in AS67 streams, allows you to shuffle them, delay them, and then we can create new AS67 streams that we then pass out, okay? So we bring that in, we shuffle it, we send it to the destination. So COTS switching, really important things here is that we're not using any SDN. We're using IGMP v3, okay? And we expect the switch to be able to action that within 25 milliseconds. And we're able to do clean switching. So clean switching is really simple. There's two modes. We can do break before make. So I have the first stream. I leave that to join the new stream, and I freeze the frame. So I have no disturbance on the video, and I might have a slight disturbance on the audio. In a TX path, I do make before break, which means that I have the first stream, and I join the second stream, and then I switch them in. In this case, you take slightly more bandwidth for this path than you do for the top path. Here, there's no additional bandwidth required. Here, you're going to have two streams at the same time in the system. So migrating a TR03 is really is one of where the customer wants to get to, and this is essentially a similar concept where we have the devices connected to the network. We take one stream, but we want to mix up the audio and the video independently. Okay, but now we want to have the streams be RFC 4175 and AS67. So being able to mix them in a singular system to the destination. Like I said, control and monitoring is very simple. And this is actually the most important statement. So from a human perspective, on the panels, the operator shouldn't care whether they're operating an IP core or whether they're operating an SDI-based core or whether it's a hybrid. Okay? The moment the operator needs to remember a multicast or an IP address, we fundamentally failed. So the control system is really important. We offer out-of-band control, which means that if you all have a security IT department that doesn't want these switches to be available on the corporate network for security reasons, we can actually break out the control layer separately. So in this case, the control and the panels go through the controllers, but they never actually speak to the media network. Okay, so we don't require the IT department to lock down the switch. It's a bit like buying a Ferrari and then running it in first gear. So for us, this needs to be a completely non-blocking high-performance network, so we're able to do out-of-band control as well as in-band control. And for this project, we do it as out-of-band. Clean and fast switching like SDI, so the ability to switch must be very, very quick. And when we come to deploying the system, we're able to take all of the edge devices and discover them, and we're able to bulk address the IPs and also the multicast throughout the whole system. So being able to add devices in the system is very simple and easy to do. And like I said, we should be able to do multi-level breakaways. So for this project, we had a northbound interface to an overarching control system that was lab over VSM. We had to provide drivers for Grass Valley Camera, the Studio Dante desk, and the Harmonic service to allow us to route into them on the IP. And we provided critical monitoring of the whole system, and we provided a northbound interface into Skyline Data Miner so the customer could monitor across the whole facility. So when you look at it, it's a fairly simple topology. You have your devices, a mixture of SAM and third-party devices. You then start breaking down into the essence types and what's available, and you can see why you have to have a migration plan when you want to go from Dash 6 to, in the future, 2110. But we also allow us to manage the routing at the IP core, which is very critical to managing the switches and the switch time. But we're able to provide a simple northbound interface to the overarching control system to manage us. So just a couple of closing comments. For this project, we did provide a full portfolio of gateways, switches, processing, servers. We did provide the switches. So we provided the Juniper and also the Arista switches. And that was really to guarantee the performance of the IP core. We also provide the third-party drivers. So to be able to route IP signals back to the Grass Valley camera, you need to be able to control the camera. to route live signals into a harmonic server for playout is also quite important, and to be able to route audio back and forth as well. To give you an idea of the size of the system, it's 2,400 IP ports. That's a lot of streams that are flying around the system. So one of the things that we have to be able to do is be able to build these systems and build them to scale, okay? It's a lot of information. Thank you very much for your time. What I would say, we're running these sessions every day. Please make sure you grab one of the booklets at the front there. Gives you a good overview of the sessions that are coming up later today, and also the sessions over the next couple of days. Thank you very much. If you have any questions, I'll quite happily take them at the end. Thank you.